Welcome back. We continue with our study on groups and the other algebraic structures. So we had begun looking at groups. We had defined what a group is and the four axioms. So we continue to look at the four axioms of a group. Now we said that for a set, a given set to be a group, supposing we have set A, supposing we have this set A of elements, and for us to show that this set of elements is a group, we say that this set must satisfy some conditions. So the first condition that this set is supposed to satisfy is a condition of closure. And so by closure, what we meant was that if you take any two elements, and supposing this group, supposing it's a set, this set is a group under addition. If you take any two elements and add those two elements, the answer that you get must be a member of this set. The answer that you get must be a member of that set. That's what we mean by closure. So that is if the set is considered as a group under addition. But if you want to consider it as a group under multiplication, what you mean by closure is that if you are to pick any two elements and multiply these two elements, the result that you get must be a member of that set. So if that happens, then you say that this set is closed under multiplication. Now, the other property was associativity, and we said that associativity will always follow if the other properties are verified. But by associativity, what we mean that under addition, if you pick any three elements, A, B, C, from this set, and then add those three elements with the bracket in this position, the answer that you get must be the same as this answer when the bracket is shifted to this other position. So this is what we say, that the set is associative. The set is associative if it fulfills this condition. For instance, if you have 2 plus 3 plus 4 with the bracket here, the answer will always be the same as 2 plus 3 plus 4 if the bracket changes position. So this answer will be 9. Is that okay? So we say that this set is associative. Now the other property, and that is what we'll be looking at today, is that every element must have an inverse. Every element must have an inverse. So that is what we'll be looking at today. And the other property is that the set must have the identity element. Must have the identity element for it to be a group. Under addition, the identity element is 0. Under multiplication, the identity element is 1. So for instance, this set has a 0, and so can be considered as a group under addition because the identity element is there. Under multiplication, we say the identity element is 1. So we looked at multiplicative groups. For instance, when we talk of this set with a star, it means we've removed a 0, and we are only considering elements which are relatively prime to the number here. So for instance, supposing I take z raised to star mod 8, this is a group consisting of elements 1, 3, 5, and 7. So we can verify that all the 4 conditions of a group are satisfied by this set. For instance, when you talk of closure, under multiplication, 3 times 5, mod 8. This will be what? 7. Is that okay? And 7 is a member of this set. 7 is a member of this set. So this set is closed. You can pick another element. 5 times 7, that will be 35. But 35 mod 8 If 8 were to go there, the remainder will be 3. Is that okay? The remainder will be 3. You can see 3 is a member of that set. That's what I mean by closure. Every time you pick any 2 elements and multiply them, the result that you get must be a member of the set. Is that okay? That's what I mean by closure. So this set can be considered as a group under multiplication. The identity element is there. 1. The set is closed. Associativity will follow because we are talking about multiplication. Associativity will follow. For instance, if you take 1 times 3 times 5, this result will be the same as 1 times 3 times 5. So it will follow. Associativity will always follow. Now, so what we now want to find out, do all these elements have inverses? Do all these elements have inverses? That is the only thing we are supposed to check. Now, so for instance, the inverse of 1 is 1. Under multiplication, the inverse of an element, A, is B if the product is 1. Under multiplication, the inverse of L is B if the product of these two is 1. Now, we are talking about mod 8. So the inverse of 1 is 1. What about the inverse of 3? What element, when multiplied by 3, gives you 1? That is the question. What element, when multiplied by 3, gives you 1 in this set? So what we usually do, we use an extended Euclidean algorithm to find the inverse of 3. Is that okay? Use extended Euclidean algorithm. So normally we would say 3 into 8 would be 1, and the remainder would be 2, and then 2 into 3 would be 1, and the remainder would be 1. So you would reverse. You would reverse and then find the inverse of 3. But then we have the Rust code that will be doing this for us. The Rust code. So when you write the Rust code, again, those are the steps you want to follow. Now, so I want to begin by looking at computing inverses for an additive group. An additive group where we are using the addition sign. So that one is very easy. Then we shall go to how to find inverses for multiplicative group. Now, so what is an inverse of A under addition? Under addition, the inverse of A is B if the sum of these two gives you the identity element 0. Is that okay? If the sum gives you 0, then we say that these two elements are inverses of each other. For instance, let me take Z8. This one does not have a star. So if it does not have a star, it means we are considering all the elements from 0, 1, 2, all the way up to 7. We are considering all those elements. Is that okay? Yes. Now, what is the inverse of 1? The inverse of 1 is that element which, when added to 1, gives you 0. What element is that? 7. Is that okay? Because 1 plus 7 is what? 1 plus 7 is 0. Mod 8. Mod 8. So if 8 were to go, because the answer you get here is 8. So if 8 were to go into 8, the remainder will be 0. The remainder will be 0. Now, so what is the inverse of 2 in the same group? The inverse of 2 will be what? Will be 6. Is that okay? 2 plus 6 gives you 0. So the easier way of doing it, if I'm given Zn and I'm asked to find the inverse of 2 in Zn, I will take n minus 2. That's the easiest way. So for instance, in this case, when my n was 8, and I was asked to find the inverse of 1, I took 8 minus 1, and I got that the inverse was 7. Is that okay? And in this case, when my n was 8, I took 8 minus 2 and gave me the inverse as 6. So if the group is an additive group, it's very easy to get inverses. Just subtract n minus the element you are considering. Now let's look at the example 69. Example 69 says, find the inverse of 7 in Z19. That Z19 does not have a star. So it means that is an additive group, because the identity element there is 0. 0 is still there. Is that okay? What is the inverse of that 7? Should be what? 40? Is an additive group. Just take n minus the element. Our n in this case is 49. 49 minus 2 minus 7. No, it's, our n is 19. Eh? Yes, our n is 19. 19 minus 7 gives us what? 12. That is the inverse. That is the inverse of 7. So that's how you do it. So in fact, if you are to write Rust code, it's very easy. Just need to take n minus a. Is that okay? N minus a gives you the inverse of a. So just be changing n and a. That gives you the code. Now, so that's a very short code, and it's here. I've written the code for find the inverse of an additive group. It's just a small thing here to take care of the negative sign. Take care of the negative sign. Of course, you can omit this part. You can omit this part. But if you omit it, then it will not take care of the negative sign. This is supposed to take care of the negative sign. Now, let me just explain what I mean by that. You see, one the inverse of A. And addition, we know that the inverse of A is n minus A. So if A is positive, then you get the answer straight up. Is that okay? But if A is negative, then you need to add this part, then add this part. Take care of the negative sign. Because supposing I have, supposing my A is -7. Supposing this is my A, and supposing n is 19. And I want to get the inverse of -7. Is that okay? Of course, the inverse of -7 is supposed to be 7. That is the inverse of -7. Supposed to be 7. Now, without this part and this part, if I take n, then minus 7, it will give me, this is 26. This is 26. Is that okay? So that is now this part has to come in. If this part comes in, it reduces 26 mod 19. Gives you 7. Is that okay? If this part comes in. But now, what about this part? What about this part? If I have -7, then I say, you see this part, what it means? What this part means, this part, just this small part. This small part means the remainder of A on division by N. The remainder of A on division by N. That's what it means. The remainder of A on division by N. So for instance, if A is 19 and N is 9, then the answer here is 1. Is that okay? That's what it means. The remainder, so you just write the remainder. That's what that part means. So what is the remainder? What is the remainder of -7? What is the remainder of -7 on division by 18? Your Rust code is supposed to understand what it is. It's supposed to understand what that one is. It's supposed to understand this, that the answer here is 11. It's supposed to understand that the answer is 11. So we're asking ourselves, if 18 were to go into -7, what would be the remainder? So if 18 goes in -7, the remainder will be 11. Is that okay? The remainder will be 11. To go there -1 times. So 18 into -7, go there -1 times. The -1 times that will be -18. When you subtract, the answer will be 11. So the code must understand this part. It must convert it, first of all, to positive. Convert it to positive. So that is why this part is important. This part is to convert that negative number to positive. So that if I have 19 minus -7, and the -7, okay, then I say remainder of that 19, then the whole thing again, I get the remainder to negative when I divide by 19. So that is, the last part is just to take care of, supposing what is inside is bigger. Supposing what is inside is bigger than 19, it will reduce it. That is why this outer part is important. Is that okay? So for instance, in this case, what was inside the bracket became 26. So 19 was to work on it. Is that okay? Yes, 19 was to work on it. That is how we write that Rust code, but it's a very small thing. You would have omitted that other part. I was just explaining why that other part is also important there, because we'll be dealing with the negative numbers. And you can see my A is an I32 number. It's an I32 number. It means A can be negative, A can be positive. Is that okay? Yes, A can be negative or positive. That's why what you mean by I32. 32, those are 32 bits. So we're dealing with both negative and positive numbers. Now it's very easy getting those inverses under addition. So I want us to get inverses under multiplication. Oh, okay. So I wanted to just to run the code to just see how it runs. These are very simple code. Can you see it? The code. Huh? You cannot see it, eh? Yeah? It's not, okay. It's not showing on the, what's, okay, let me again share it. What about now? You can see it, eh? So it's a very simple code, just the way you're seeing it. I have my A is 7 and my N is 19. So when you run, it tells you that the inverse of that is 12. So when we remove this, you see this outer part is the one that is supposed to reduce it to 12. It's supposed to reduce that to 12. Now, so for instance, our A could be -7. Our A could be -7. So that is why I say that division is important for the negative numbers. Let's just try -7 and see what it gives us. So it tells us that the inverse of -7 is 7. But now when you remove this outer part, let's see what it will tell us. Just remove this part and see what it will tell us. It has run with the warnings and given us 26. So it was not able to reduce. It was not able to reduce. The warning was because of. So I've returned it. So it was not able to reduce it. So the outer one is supposed to reduce whatever is inside the bracket. If whatever is inside the bracket is bigger than n, then it's supposed to reduce that. Let's try to remove this one and see what it will tell us. It has given us 7 in this case. Okay, it has given us 7. What about if the number was, let's increase the number. Let's increase the number and see what it gives us. Okay, it has still run, it's still okay. So in fact, without the one inside, the outside will still work, do the same thing. It will still work. But they are meant just to deal with the negative numbers. They convert those negative numbers to positive. So like when I put it there, I expect it to convert this negative A to positive. That's what I expect. Give me a remainder which is positive. Now, when I removed it, still worked because it was doing whatever is inside the bracket. And then this one will still work, convert, divide, and then give us a positive remainder. So that is why we still got a correct result. Now let's look at not this one. If it's a multiplicative group, and let's look at multiplicative group, how to get inverses. That is something we've done before. Now, so I'm considering this group mod 42. Of course, these are a group of relatively prime integers less than 42 and greater than 0. So this will be relatively prime numbers. Now, so the question is, what are the inverses of these elements? Of course, we know that this group is closed. And if I multiply 17 and 19, I would get another element of this set. If I multiply 25 and 29, I will get another element of this set. So it's closed. Is that okay? Yes. So the question is, what are the inverses? Now, so we get the inverses the same way we were getting earlier. The inverses of the elements of the group. Get them so for instance, if I want to get the inverse of 41, I would still do the same thing we used to do using the extended Euclid's algorithm. I would take 42 divided by 41. It goes there once and the remainder will be 1. Then this 1 into 41, the remainder will be 0. So I just reverse this. I just reverse this equation. When you reverse that, you get that 1 is the same as 42 minus 41 multiplied by 1. This is the same as 42 plus 41 multiplied by negative 1. Now, so we want the inverse of 41. That is why I've written negative inside to be with negative 1, but not 41. Now, so I want the inverse of 41, therefore, is negative 1 mod 42. But negative 1 mod 42 is 41. Is that okay? Yeah? So the inverse of 41 is therefore 41. The inverse of 41 is therefore 41. What about the inverse of 7 in this group? And again, this is a group. We know what this group means. Is that okay? What are the elements of this group? What are the elements of this group? 1, 2, 3, all those integers up to 18, all of them. Is that okay? Because they are all relatively prime to 19. Is it a multiplicative group or an additive group? This is a multiplicative group. Is that okay? Because it has the identity 1. It cannot be considered as an additive group because it has no identity, additive identity, 0. Is that okay? Now, so yeah, this one is as a star there. Now, if you want it to be considered as an additive group, you remove this star and then include 0 among the elements. It becomes a group under addition. Now, but the question is, what is the inverse of this 9, 7 here? We just do it the same way we've been doing, using the standard Euclidean algorithm, and then reverse. Then reverse. And that gives you the inverse as negative 7. No, negative 8, which is 11. Is that okay? Yes. Is there anybody who doesn't know these steps? Then you've not met before? You know these steps? And you? It's okay. So we just reversed those steps. So we have that. So using the same logic again, we can get the inverse of 364 mod 765. This again is a multiplicative group. In that inverse, when you do, this is the extended, the Euclidean algorithm up to there, where the GCD is 1. And then when you reverse, you get your inverse as 124. Now let's look at how the Rust code works to get that. So the Rust code begins with the extended Euclidean algorithm. And then this part for the universe, then the main function. Now, so the main function calls on the inverse, calls on the modular inverse. And the modular inverse calls on the extended GCD. And then the extended GCD begins finding the GCD. After finding the GCD, it reverses to find X and Y. Is that okay? Yes. And then this inverse function takes over to find the inverse. And then the answer is printed. Now, so that is how implementing this way becomes easier. I'll show you how it calculates so that it becomes easy for you to implement it to get the inverse. Is that okay? Yes, I'll show you how it works. But before that, let's just try to run it. Let's try to run it and see. You can see it, huh? So in this case, our A is 5 and our M is 12. So we are talking about the inverse of 5 in the group Z star mod 12. Is that okay? Z star mod 12. That's what we want. So we want to find the inverse of 5. And of course, the inverse of 5 only exists if 5 is relatively prime to 12. If 5 and 12 are not relatively prime, then the inverse does not exist. Is that okay? The inverse does not exist. So when you run this, it tells you the inverse of 5 would then be 5. The inverse of 5 would then be 5. And let's try a number that is not relatively prime to 12. Like 8. 8 is not relatively prime to 12. Let's see whether it can give us the inverse of that. It says the inverse does not exist because those two numbers are not relatively prime. Is that okay? They are not relatively prime. Now, 7 is relatively prime. Let's find the inverse. That one it must give us. Now, it tells us the inverse of 7 will be 7. The inverse of 7 will be 7 mod 12. Now, we can increase these numbers. We can increase. Let's now increase the numbers. Of course, when we increase and find that it's going beyond, we can always change our I64 to 128. And again, if we go beyond that, you can still change that to big unit. Is that okay? I'll still change that to big unit. Now let's try to run this and see. I don't know if they are relatively prime, but if they are relatively prime, then it will give us the inverse. And if they are not, then it will not. It has not, and it's telling us something. Oh, it's beyond the I-164. Is that I-64? It's beyond that. So that one, it means we can just try and change this to 128 and see whether it works. Let's just change that. So we want it to handle bigger numbers. That is why we are changing to bigger bits. Then they still here. So we can change this also. But you see, since we are talking about I, you see the range is not too huge. Even for 128, the range is not huge because of the I. But if we'll be talking about U, then we'll be talking about bigger numbers. Now let's try to run this and see whether it runs. Now this one has run and has given us the inverse. So the inverse is there. It's a big number. That is why I-64 could not manage, but 128 has managed. Now, as we've always done, we can always change this to bigger units to handle even bigger numbers. Now, so I just want us to look at how this code then works, how it works, so that it can be easier for you even to implement it. Now, so we want to see how the extended GCD function works. Then look at how the function for mod inverse works. And then once we have seen how they work, then it becomes easier for you to write this code. Is that okay? Or even for you to write something similar to do other functions. Okay, of course I have one here for if supposing the I-128 will not have worked, I said we can use big units instead of I-128 or instead of I-64 so that we can handle bigger numbers like the one I have here. Like the one I have here, this code can work out the inverse of this number. And even others bigger than this can still give us the inverse. So this one we'll look at it later. Now it's just the same code. It's just the same code. We're only changing where there's I-64, we just change it to 128. Is that okay? Or we change it to big units. And where you're using big units, and then you have to bring in these libraries that will be assisting you to do that. The first library will just be assisting you to be able to do operations on large numbers. Is that okay? Yes. And the second library is just helping you to handle 0 and 1. How to handle 0 and 1. And then the other library is assisting you to convert this big number into a string and back to a big unit. Is that okay? So that it must be in a string form, then back to big unit. So that is what those libraries be doing. Now, so let's look at how the extended Euclidean algorithm works for this code. And I've written it here. Let's just look at it. I've written the part for the extended GCD part is. Now, this is what it says. First of all, A is an I-64 type. B is also an I-64 type. And then want the GCD of these two numbers. And the result will be, this is the GCD of those two numbers. Is that okay? And the GCD is also an I-64 type. And this is A and that is B. Now, so in cases where B is 0, so you have A and B, you want the GCD. And supposing B is 0, that's why it says if B is 0, then it will give you A as the GCD and the coefficient of A, 1. And the coefficient of B will be 0. You see, the extended Euclidean algorithm always writes the GCD of two numbers in this form. It writes the GCD in this form. so that the GCD of A and B can be written as A multiplied by X plus b multiplied by y. Is that okay? That is what it does. So what this code is telling us at this point is telling us that in cases where b is 0, then it means even its coefficient will be 0. Is that okay? If b is 0, its coefficient will be 0. And then it's telling us if b is 0, then the GCD of these two numbers will be a. The GCD of these two numbers will be a. And the coefficient of a will be 1. The coefficient of a will be 1. That's what it's saying. So that you can write a is equal to a times 1 plus 0 times 0. Is that okay? Yes. You can write GCD in terms of a times x plus b times y, where b is 0, y is 0, and x is 1, a is a. So that is what it says at that point. Now, else, that is in cases where b is not 0. In cases where b is not 0, then what happens? When b is not 0, you began with a, you wanted the GCD of a and b is not 0. So the first thing it does, it calls for the GCD. It calls for the GCD of b and the remainder of a on division by b. It calls for GCD of b and the remainder of a on division by b. Is that okay? Yes. That's the first thing that happens. And this continues until b becomes 0. This process continues until b becomes 0. When b becomes 0, you go back here. Go back here. And it has told you that when b is 0, then the GCD becomes a. Is that okay? The GCD becomes a. Is that okay? Yes. Let me just show you a small example, what I've just explained. Just show you a small example, what I've explained. Just here, up to the point of getting the GCD. This other part is forgetting the coefficients x and y. This other part is forgetting the coefficients x and y. Now let's take, for instance, 16. I want to take a to be 16 and b to be, let me say, 5. And I want the GCD of 16 and 5. The program has discovered that b is not 0 in this case. So you're beginning from this part. You're beginning from this part. So we want the GCD of a and b, but it calls for b. The first call will be the GCD of b, which is 5. And then the remainder of a on division by a on division by b. The remainder is 1. That is the first call. Is that okay? The second call, this happens until b becomes 0. So in this case now, this is our b, which is 1. Is that okay? So we go the second call. The second call, it will now call for the GCD of 1. And then that is our b. And then A divided by B, the remainder of that. Our A is 5 this time. Divided by B, the remainder is 0. Is that okay? So B has become 0. When B is 0, you go back here. It tells you what becomes of the GCD. The GCD is A. Is that okay? So our A this time is 1. So it means the GCD therefore is 1. The GCD is 1. That's what it's telling us. The GCD is 1. It does not tell us that one only. It even tells us the coefficient of A. When B is 0, the coefficient of A will also be 1. So this is what it will print. Begin going back. Let us begin going back. So it now begins going back using with these values until it gets the coefficients of x and y. That's amazing. I want to charge. Let me charge this. You stopped recording. Yeah? No, I'm saying it's not recording. Oh, pause it a bit. Oh, maybe you want another example so that you understand it. Huh? Give another example. Okay, let's look at how it works. So I want to give an example how it works to get the GCD and then get the coefficients. Let me just create some space. Okay, let me use this space. So supposing I want a GCD of, let me say, let me say the GCD of 18 and 4. This is the GCD that I want. Is that okay? That's what I want. 18 and 4. Of course, you know what that GCD is. Want to get the GCD, so there'll be initial call. Initial call is for the GCD of 18 and 4. Is that okay? That's what we want. So this is what you input in the main function. And then it calls the first call. First call will be for the GCD of B. Is that okay? And the remainder of A on division by B. The remainder of A on division by B. So I have this A divided by B. What's the remainder? Yeah? This will be 2. The remainder will be 2. Is that okay? Good. Then there's another call until B is 0. Until B is 0. So there was next call. Next call, because B is no longer 0. So again, this will be B. Is that okay? And then the remainder of A on division by B. What is the remainder there? 0. So it has achieved B is now 0. Is that okay? When B is 0, A becomes the GCD. Is that okay? A becomes the GCD. So our A is this. Our A is this. Is that okay? So what will it print? Suppose, therefore, to print the GCD, the coefficient of A, and then the coefficient of B. Is that okay? Yes. We'll print that. That's what it said. It said, when you look at the code, it said, if B is 0, then the result will be A, and then 1, 0. That will be the result, where A is, so you see in this case, our A is 2. We are looking for the GCD of 2 and 0. Is that okay? The GCD of 2 and 0. So A is 2 and 0, B is 0. So the coefficient of A, therefore, is 1, and the coefficient of B, therefore, is 0. Now, so this is how we get the GCD. Now, how do we then get the coefficients? How do we get the coefficients? The formula is this. The formula says, from this result, we know what X is, and we know what Y is. Now, we want to reverse from this step. We want to reverse from this step. We go with these values to this step. We go with those values. We got with those values to that step. Is that okay? That is where we go. What is the formula when we arrive there? The formula says our new X becomes the Y we've come with. Our new X becomes the Y we've come with. Is that okay? Huh? The Y we've come with is now our new X. In this case, we've come with a Y which is 0. So our X is 0. Is that okay? Good. What about Y? What does Y become? Y becomes the X we've come with minus A divided by B multiplied by the Y we've come with. Multiplied by the Y we've come with. Is that okay? I'm referring to this point. We've come to this point with these values. X and Y. These are the values we've come with. So that means our Y therefore becomes the X we've come with, which is 1. Is that okay? Which is 1. So we are at point 42. At point 42. That's where we are. Our A is 4. B is 2. When you divide that, you have 2. Is that okay? Then multiply by Y that will come with. Multiply by Y that will come with. And the result you end up with is 1. The result you end up with is 1. So this is our new Y. This is our new Y. What do we now have? What do we now have? Because we want to proceed to the next point. Want to proceed to this point. But what do we have? What we have is the GCD. We have an X, which is 0, and we have a Y, which is 1. Is that okay? Yes. We move with this to the next point. We are reversing from the bottom going up. Is that okay? As we always do, we reverse from the bottom going up. So we're now going up with these values. When we reach there, our x becomes the y that will come with. Which y is that? Y will come with the 1. So our x becomes 1. Is that okay? What about y? Y becomes the x that will come with, which is what? 0. Is that okay? Which is 0. Then minus a, which is 18, divided by b, then multiply by the y that will come with. What is 18 divided by 4? And you only take the whole number. 18 divided by 4 is 4. Is that okay? So this result is -4. That result is -4. We've reached the end of that. So what do we now have? What do we now have? What we now have is the GCD, which was still 2. We have a new x, which is 1. And we have a new y, which is -4. And so this means, therefore, that our GCD, which is 2, can be written as 18 multiplied by 1 plus 4 multiplied by -4. This is -4. So -4 and 1 are our coefficients we're looking for. Is that okay? Yes, that's how that works. That is how the GCD extended Euclidean algorithm works. That's how it works. And that's how you can implement it. And when you go through these steps, you realize that the same steps we've been doing. Let me show you that they are the same steps. Look at this step. This was the initial step. But now this other step is what we normally say, 18 can be written as 4 multiplied by 4, then the remainder is 2. That 2 is what you are seeing here. That remainder 2 is what you are seeing here. And this other 4 is what you are seeing here. Is that okay? And then what will be the next step after this step? After this step, the next step will be these 2 to divide into 4. So we would then say these 2 go there twice, and the remainder will be 0. And that is the step you are seeing here. That's the step you are seeing here. So the remainder is this 0. The one you are seeing here is the remainder. This is the remainder. And this 2 is what we had here as the product. Is that okay? So they're just the same steps. And then after that, you begin reversing from where the GCD is. The GCD is 2. That's why you begin reversing. You don't begin reversing from here. So reverse from here going up. So just the same steps. Now let's look at how the inverse function works. We looked at how the GCD works. And the GCD would work and give us the GCD and then give us the coefficients. Is that okay? Just the coefficients. So from there, the inverse function picks up. And then it's supposed to give us the inverse of that number. It's supposed to give us the inverse of that number. Now, so if you've not understood that how the GCD function works, there's another example I've given in this notes. You can look at it slowly. Then I think you'll understand. But I've already explained, before that example, I've already explained what the code is about. This part, I've already explained what this part means. This part means that if one of the numbers is 0, then the GCD becomes the other number that is not 0. So that is what it means. And in the case where now none of the numbers is 0, it begins making calls. Is that okay? It begins making calls to find the GCD. And this is what I've said. It makes the call to find the GCD of B and the remainder of A on division by B. So that call will continue until B is 0. As long as B is not 0, the call continues. Is that okay? So the call continues until B is 0. And then if once B is 0, we begin now calculating for X and Y. And these are the formulas for calculating X and Y. X becomes Y. Is that okay? Yes. And Y becomes X minus A divided by B. So you're going up and you identify what A is and identify what B is, that point. Now, mod inverse function is here. Mod inverse function. So for this one, you see what it's doing. It will be using the function above. Just using the function above. The one above has already found the GCDs. And this one talks of if the GCD is not equal to 1. That is what this symbol means. This symbol means if GCD is not equal to 1, then there is no inverse. Is that okay? Yes. So you see, the one above has already done the GCD. If the GCD, where the GCD was 2, it means that the GCD is not equal to 1. Is that okay? Yes. So if the GCD is not equal to 1, this one will automatically write that no modular inverse exists. Now, where the GCD equals to 1, it has to write the sum result. Look at the result. It has taken X. That was the coefficient of A. It has taken X. So you see that the one above had calculated for us the GCD, then the coefficient of A as X, and the coefficient of B as 1. So when this one discovers that that GCD was 1, then it picks that X, which is the coefficient of A, and then divides it by M. Writes the remainder of X on division by M. That must be a positive result, must be positive. But where it happens to be negative, where on adding X, when on division by, supposing X is negative in that case, if X is negative, you see, if X is negative, supposing I have negative 2, and I divide it by 5 and write the remainder, this remainder will still be negative 2. Is that okay? That remainder will still be negative 2. But we want it to be positive. So to make it positive, you add M to it. You add 5 to it in this case. And the answer becomes 3. If this answer happens to be bigger than M, divide by m, and write the remainder. Is that okay? It happens will be bigger. Divide by m, and write the remainder. That's what this part means. So this part, as I had explained in the earlier exam, is meant to take care of negative x. If x happens to be negative, then this is what will handle it. Because if x is negative, this part will give us a negative value. It will be negative 2. So how do you make it positive? You add m to it. If you add m to it, you get a positive 3. What if it was bigger? What if the value inside would be bigger than m? Reduce it by m. Reduce it by m. That you write the remainder. So that is what the inverse function is doing. Actually, this inverse function is not doing a lot. It's just using the results above, checking the one that gave you a positive, that gave you 1 as the GCD, and then takes the coefficient and converts it. Now, this part I've said what it means. This part says if the GCD is not equal to 1, is not equal to 1. So that is what that part, that symbol means. Now, let me just now explain using this so that then we end. I have those two values, 31 and 60, and I want to find the inverse of 31. So you put this in the main function. The main function calls on the inverse function. Is that okay? And the inverse function calls on the GCD, extended GCD function. And then the extended GCD function begins now finding the GCD and then the coefficients. The inverse function will just pick the coefficient if it discovers that the GCD is 1. Just pick the coefficient of x. The initial call is for that Is that okay? Then there is now, since the p is not 0, there will be another call. And the calls continue until p becomes 0. So since p is not 0, we now call for b and the remainder of a on division by b. 31 divided by 60, the remainder is 31. That means this is the call. 60 plus 1 is the call. B is not 0. B is not 0. So there will be another call. And that call will be B, and then the remainder of A on division by B. Is that okay? B, which is that 1, the remainder of A on division by B. And this remainder looks like 29. So this is the call. Is that okay? Good. Now B is not 0, so again there must be another call. What is that call? 29, which is B. Then the remainder of A on division by B. The remainder of A on division by B. And of course, this remainder is 2. That is another call. Is that okay? B is not 0. So there must be another call until B is 0. So what is the call? Now B becomes A. Now B becomes A. B becomes A. And then the remainder of A on division by B. When you divide this by B, the remainder is 1. So this is the call. Is that okay? B is not 1, B is not 0. So the process continues. So B becomes A. And then A on division by B, the remainder here definitely is 0. So B has become 0. So since B is 0, our A at this point, therefore, is the GCD. And A at this point is 1. So the best case tells us, therefore, that our A becomes the GCD, and the coefficient of that A is 1, and the coefficient of B is 0. That's what the best case tells us. Now we found our GCD, we found our X and Y. So now reversing process begins. The reverse process begins. So we go here. Is that okay? Go there. When you reach there, you're going there with these values. When you reach there, X becomes Y. X becomes 1. And what is Y? Y is what? Y is 0. Is that okay? X becomes 1 and Y is 0. What becomes of Y? What becomes of Y? Y becomes X. The X that you come with, is that okay? Minus A divided by B multiplied by Y that you come with. The X that you come with is 1. And the point we are referring to is 2, 1. That's the point we are referring to. So our A in this case is 2, and B is 1. And then Y that it comes with is 0. So that Y becomes 1. Is that okay? You pick those points and move to the next point, 29, 2. Then what you get there, move with it to the next point, 31, 29. 31, 29, the next one. Then what you get there, move with it to the next point up, which is 60, 31. And 60, 31 is what you began with. So when you reach there, you stop. You read the values. Because you've reached where you began. You began with 60, 31. The steps are there for getting the coefficients. All of them. All the steps are here. So work down. When you move the next point, the steps are there. When you move the next point, again, the steps are there. So you have to go through the steps until you reach where you began, which is 60, 31. When you reach there, just read the values. X and Y. Now, the inverse function has discovered the GCD above is 1. It has also discovered that the coefficient of 31 is negative 29. It has also discovered that. Is that okay? Yes. So it's interested in that coefficient. So it picks that coefficient then divides by 6 and writes the remainder. Of course, since that value is negative, the remainder there will be negative 29. Since it's negative 29, it adds M60 to negative 29 to get 31. Then reduces that 31 mod 60, and it will remain to be 31. So that becomes the inverse of 31. The inverse of the number we're looking for. No, so I've used the same reasoning just to find the inverse of 17. So where 17 is A and our B is 29, the initial call, is that okay? B is not 0, so the calls continue. Is that okay? Until B becomes 0. So the calls will continue. Calls will continue until B becomes 0. So again, you look at this later. Let us to have a short break.